This sequence of videos is going to go through projectile motion, which is a very important example of two-dimensional motion and is really the case of two-dimensional motion that we will talk about the most, at least right now, before we really have a handle on forces. So two of the things we'll be doing in this video is really defining what projectile motion is and what variables we use when talking about it. And then the second part is really talking about how we relate motion in two directions using time. And this is the most important idea to really have for two-dimensional motion, and projectile motion is a great example of that. So the student learning outcomes that this video ties to the strongest is actually problem solving. That really, like doing representations or communicating information, that matters a little bit, and we'll be touching on that in different parts. But the big thing is the problem solving. How do you move from having a situation to finding some sort of result? So that will definitely be happening here. So I want to start just briefly with what the definition is. And basically, when we're talking about projectile motion, we are talking about the motion of an object that is just due to gravity. Now, we already said that that was what free fall is, actually. So projectile motion is, in fact, free fall in two dimensions. And what that's normally going to look like is this sort of parabola. And the reason we see a parabola is because it's moving in x, i.e. horizontal, and it's moving in y, the vertical direction. So when we talked about free fall, we were only thinking about a one-dimensional problem, but now we're making it a two-dimensional motion by having it move sideways as well. So when you see an object move in this parabola shape, that's the idea that it's going to be projectile motion. And just like in free fall, we said that free fall was only valid if you have negligible air resistance. The same thing is going to be true for projectile motion. We'll talk a little bit more about that. Now, this is neat. This is a strobe picture. So this is an actual real picture of this tennis ball bouncing. The fact that every time it bounces not quite as high, that's something we'll talk about when we get to energy. That isn't related at all to projectile motion. So you're just focused on this parabola shape in between when the ball hits the ground. And you can see that since this strobe picture is taking a picture every whatever interval, the same time interval between flashes, this is basically creating a motion diagram. So the fact that these are closer together up here tells you that it's traveling slower here than down there. So again, the parabola tells you that it's projectile motion. Now keep in mind, a picture like this is a physical picture of space. So we're seeing x and y. This is actually a trajectory. So this is something to be careful about. As I brought up in a past video, when we start talking about projectile motion, plots of what's happening of y, up, down, versus time look like a parabola. However, if we look at a trajectory, x versus y, that also looks like a parabola. So make sure you understand what type of image you are looking at. So now, one of the first things that we need to talk about with projectile motion is the idea of launch angle. And you can think about this, for instance, of taking like a water balloon launcher, and you can aim it straight up, you can aim it horizontal, or you can aim it at some angle in between. And what's important is we usually define launch angle with respect to the horizontal. So whenever I talk about theta, I am defaulting to talking about a theta with respect to the horizontal. Of course, if I give you the angle with respect to vertical, you're able to figure out what the angle with respect to horizontal is. That's really what we talk about here. Now, why we care about launch angle is that normally when we have projectile motion, you know what your launch angle is, and you know what your initial velocity is. So we're defining this initial velocity vector in terms of a magnitude and a direction. Now, something that I brought up in the earlier videos on two-dimensional motion is that you really want to talk about components. So this goes back to just some basic vector math. If you have this vector defined in terms of magnitude, a length, and remember that we can define the magnitude of this vector as just v naught, and we'll use this notation typically, that we need now to actually define an x component and a y component, because when we set up our kinematics equations, we're going to be working separately in x and y. Now this is a situation where you probably don't want to use parallel and perpendicular, since it's actually going on a curved trajectory, so there isn't a consistent definition of what parallel and perpendicular means over its motion. So please use x and y for this, and again, the first step is typically going to be thinking about how our launch angle and initial speed, which is again the magnitude of this vector, can be broken into x and y components. Now, one mistake that I see happen frequently, and I want to explicitly state this so that hopefully you don't do it, is to take another point of its trajectory. For instance, maybe you know the highest point that it gets to. Don't take that and make a launch angle from that. I've seen students do this where basically you assume it's moving in a triangle. And there's this really interesting idea that if we didn't have gravity and you launched it at some sort of angle, it would in fact make some sort of triangle. That at some given distance, x, you would be at some specific height, y, and that would be a right triangle. However, we have gravity, and gravity is actually making it fall from that sort of triangle shape. And so if you think about that equation for y, we have, and I'm going to say that my y final equals y initial, and we then have our initial velocity in y times our delta t. And then in this case, and I know I'm jumping ahead a little bit, but we have minus 1/2 gt squared. So this is what would be giving us just that triangle, but this is falling. So we, in a way, have two pieces of motion here. We have this triangle motion, and then we have this falling motion. So if you just use some given point later on the trajectory, and you calculate your initial angle from that, that's not going to be right. You have two pieces of motion. So please be careful about that. That again, keep in mind that your velocity, and we'll talk about this a little more, is always changing, and so you don't actually have it going in a straight line. So please be careful. And again, for getting our magnitude and direction, our angle, into x and y components, you're just going to use trig relationships here, and as long as you're using this theta and not the other theta, the other angle, which would be 90 minus theta, these are your definitions for x and for y. X is cosine theta times your speed, y is going to be sine theta times your speed.